Greetings, welcome back to randomtronic. My name is Chris and today I want to show you a new multimeter. And do not let this boring plain packaging to fool you. This will be a rather interesting one. Here is the multimeter on the eBay listing, and it's a AN8002 model by Aneng. As you can see, £11.18 with free postage, so yeah, £11 with some change. That's really affordable. The item number is 292-028-519424. What's special about this? This is, apart from being extremely inexpensive, this claims to be a True RMS multimeter. True RMS for this price? I do not know. Let's have a look. This is how it came. It's clearly been mishandled somewhere along the way from between China and my house. And this is how it comes. You get K-type thermocouple, probe leads. We'll have a look at those in a moment. A little instruction, the generic box, and the multimeter in a little pouch. Pouch is nice, but completely pointless, I guess. First thing that struck me is how small this thing is. So it's really nice and, you know, handy. Small multimeter, auto ranging. And it didn't come with batteries, but I did put the batteries in here before starting the video, and yeah, it switches on and it does stuff, as you can see, through RMS. So we'll test it. There is a backlight. Sure, you should be able to see the backlight's on. Press and hold, the backlight goes off. Posts over here are a little bit wonky, but we'll see inside. The probes, they claim 10 amps, and that's about it, what they claim. 10 amp. There's a European conformity symbol and a double insulated symbol and a high voltage symbol. The little shrouds on the sharp ends, the little thing says cut to 1000 volts or cut to 600 volts without those on. Reasonably stiff. The leads reasonably soft. Nothing special. There is no markings on the leads, which is disappointing. It's just some cheap cable. And yeah, doesn't feel anything special. It's like the cheap stuff that you get. Sharpness wise, yeah, a bit painful. I've seen better, but I've definitely seen worse. Let's have a look inside, because of course the true test of what this actually is worth is going to be have a look on the inside and see what it really does. On the battery cover we've got not a self-tapper but a metal threaded insert, brass insert here, so that's really nice. And this is just cheap plastic, really cheap. I mean, what do you expect for 10 quid? I'm surprised this actually switches on. Batteries didn't come as a set. That's those are my batteries. And we've got 4 more screws, which without a doubt will be self-tapping screws. Putting 4 threaded inserts on the perimeter, far too expensive for that. That would be like half of the price of this multimeter. I've had this sitting a while waiting for the video. I just didn't have enough time to switch on the camera and do actually something with it. But yeah, I'm hoping today will be just enough time to have a look inside and see what's going on. Hopefully I won't kill it. I kind of like the format, really nice and small. It feels, yeah, it doesn't feel great, but okay. And okay, so it appears as if the whole thing will pop out if I press on the battery compartment, and voila, we are inside. And for the 10 bucks, or the 10 pounds, 10 quid I should say, and this is what you get. There is a PCB in here. There are fuses on here, which is surprising. So we've got 10 amp fuse in here and 600 milliamp fuse over here, but those are tiny. They do appear to be ceramic type, which is good, but size wise they are the smallest fuse I have seen. Let's see, so it's, yeah, 10 millimeters long and 3.5 millimeter thick. The main chip is blobbed onto PCB as expected. That's the cheap construction. There's one discrete IC buzzer, a Rubicon capacitor, which is interesting. Is that a real Rubicon? Maybe. Yeah, but it says Rubicon on there, so Rubicon. 10 amp shunt resistor, 0.01 R, and which is just a piece of wire that has been soldered into the holes. Oh, that's interesting. Here is a unpopulated switch on the back of the board, and it says range. But I haven't got range. This is auto ranging switch. So let's do experiment. It says auto, so which would be auto ranging. Oh. Okay. Oh yeah, it's changing ranges. So let me see if I can do it on camera. As you can see, you can manually range this meter just by doing a little mod. The button is there. All you need to do is get a switch on here, which is nice. Not necessarily I need it. Presumably, if I press and hold it, it will go into auto ranging. Yeah, there we go. So pressing and holding that hidden switch goes into auto range mode. If you press it, it will go through the manual ranges, which sometimes comes handy, but we'll see how quick the auto ranging on this meter is. More self-tapping screws in here holding the FR4 PCB. It is a fiberglass PCB, no problem there. What are we taking out? All those? There we go. So over here we have some grease, I guess, on it's a little bit, yeah, there's some grease for the contacts of the range switch, and the plastic glass, it's unglued, it does just come out. This is super crappy. This is, yeah, I'm surprised if it's gonna last, but it's in those plastic little tubes, so technically it should last for some time. Look, the whole thing fell apart. So it's a cheap meter. In terms of protection, there are those two fuses, but that's about it, nothing else. Just putting this together now, I've noticed that there is a double lip on the blue part of the plastic, which then accepts the gray part of the front plastic piece, and that basically goes in. If I just put it right, it gets trapped between those two lips all the way around, which is a good attempt actually of trying to make this a little bit more explosion proof, but the quality of the plastic itself is not too promising, so small explosion possibly, but yeah, with those little fuses I wouldn't be poking this at anything with too high of energy. A small battery operated stuff, or on your bench from a power supply without some large inductors or capacitors, yeah, that's fine. I'm sure it will do the job. But more interestingly, will it measure true RMS? So true root mean square. Normally true RMS multimeters are quite expensive, but this one claims to be true RMS. Oh, that's nice. You can, if you just overstretch it, it shuts itself shut. It's a nice design. Aesthetically, it's a nice multimeter. Okay, I've just noticed between hertz, also between frequency measurement and the amps measurement, I can get it into volts, which is the same as this, I guess. No, volts, millivolts, yeah. So it will go into millivolts mode. Yeah, that's a little bit, oh. Okay, it does that here as well. So between amps and milliamps. Yeah, pretty much anywhere on this side. Okay, not a big deal. As long as you click it once rather quickly, it doesn't do that. Let's see the continuity thing. Here is the little... I don't understand, why do they put those in the test leads when they're new? I mean, this is just a waste of plastic. Okay, so let's put that here, put this here, and let's see, will it make buzzing noises? Do we have to select buzzer? Yes, we do. So by pressing once, and it's reasonable. Maybe let's take the little shrouds off. I can... If I try, that's actually not bad. If I try really hard, I can get it not to react, but yeah, it's not too bad and the sound is not too annoying, so okay, that works. At least as a continuity tester, that's reasonable. Normal meters that do not have the True RMS are normally tuned for a sine wave. On whenever you're in the AC mode, it will measure a sine wave which is supposed to be 50 Hz, and then from a lookup table within the chip, or yeah, it's calibrated to tell you what the actual value is. For most cases that is just fine. However, whenever you're trying to measure something that is not 50 Hz or is not a sine wave, the meter that you're using, if it's not True RMS, will not give you the appropriate value. So let's do some measurements. And I've got a transformer here. This is actually an old style Nokia charger. Who remembers those? All there is inside, it's a transformer, 4 diodes, so a full bridge rectification, and what appears to be here, this is, I think, a thermistor. I think no smoothing cap, although there is a provision for it. What I did is I took 2 thin wires and I tapped directly off of the transformer here, so we'll get the full AC out before the rectification. And I need to put this together really quickly because the way this assembles is, yeah, it has to be in one piece before plugging into the wall. And I also have an Arduino here. Basically all it is, the pins that support pulse width modulation, PWM, on as output. So I've got pin 3, 5, 6, 9 and 10. Those 5 pins I've written values of 0, 63, 127, 191 and 255. So that should correspond to pulse width of 0, 25, 50, 75 and 100%. You should be able to see, let's see, pin 3, or pin 3 is clearly nothing. Pin 5, you can see that's 25%. You can just about see on the screen. 6 is 50%. Where is 9? There is 9. That's 75%, and 10 is just high. And we can use those to compare measurements. Arduino oscillates, I think, on just about 490 Hz from what it said over there. So let's have a look. We can measure on pin 6. No, actually I'm measuring just under a kilohertz. I'm measuring on pin 6 on 50%, so it will be a good test to measure trueness of the RMS. So we're going to take a measurement with standard AC non-true RMS multimeter, with the RMS multimeter and calculated value. So we'll try to calculate what should be the value of the true RMS of those signals. And what we will have a 50 Hz full AC signal sine wave. We will have the same sine wave going through just a diode, so this will give us half bridge rectification. I'll just draw half the waveform on here as a symbol. Then the same 50 Hz sine wave with full bridge rectification, so it'll be all positives. Then we've got a square wave. I should draw a square wave here. Kilohertz approximately with 25, 50 and 75% duty cycle. First, let's do the 50 Hz. So I've got this modified Nokia power adapter. This plug outputs full wave rectified already, so I don't have to do anything. And the one on the transformer, I can measure either directly on the pins, so that will be AC, or I've soldered on 1N4007 diode onto it, just to get just a half bridge rectification over here and see what kind of voltage we get out of it. The first one to do the test will be UT33D, and that's non-true RMS multimeter. Let's go into volts AC. So we get on AC, on the output, we get precisely 10 volts. So 10 volts, let's write it down. If I measure after rectification, we get 9.7 volts, let's call it 9.7. This is of course the open circuit voltage. There is no regulation over there. The voltage will drop significantly once you connect a load to it, but that doesn't matter for the purpose of this test. Full wave rectified, 19.2, 19.3 AC. If I try to measure this on DC, now it's showing 9.18, 9.2 volts. So with a half wave rectification, just single diode, we get 4.24 volts on a DC measurement. So 4.2, and here it was 0. So let's do the same measurements with True RMS. Okay, so we've got the Aneng AN8002, a True RMS multimeter, so it claims. So let's see. Okay, 10.41, 10.4 volts, measuring AC True RMS. So let's write that down. Not far off. This is about right, because this meter would have measured as well accurately, and that's expected. So we'd write 10.4. When the meter is not True RMS, it's tuned to a 50 Hz sine wave, so it shows more or less accurate measurement on when measuring that sort of thing. We should start seeing difference when going into half wave or full wave rectification, and of course in the square wave that should be completely off. Okay, half wave, we get 6.01 volts. So after just one diode, we get 6.01. So there you go, almost 2 volts difference. So full wave rectified, 4.3 volts, True RMS value of the measurement of the full wave rectified. I'm surprised that, yeah, we get from 10.46 and 4 volts RMS quite a bit less, whereas here the value was increasing. And yeah, so we'll have a look when we try to calculate what that should be. Yeah, that's what it is. Okay, just for kicks, let's try to get this meter into DC. In DC we should get more or less the same values as over here. If we try measure this, yeah, it will be nothing because that's AC voltage. If we try measuring here, 4.45, 4.46, so close to this 4.2 value. Full bridge rectified, 8.93. So again, very close. AC measurements are completely off. Sine wave was just fine. Couple of tenths of a volt, who cares? When it's rectified, yeah, the difference is quite significant. This is 30% off, and this is miles off. Full bridge rectification, this is almost 5 times the value. That's interesting. Let's try the 1 kHz signal. 5 is 25% value, and it's showing 2.3 volts on AC measurements. So 6 is 50%, is showing 4.5 volts, then 9, 6.5 volts on AC. This is interesting because I'm powering this up from AC voltage, from DC 5 volts. So yeah, it seems it's a boost converter, 6.6 volts, pin 5. So that shows me 1.6 volts, and that's the 25%. Pin 6 should be 50%, and we get 1.95. And pin 9 should be 75%, 1.74. I've discovered a weird quirk with this multimeter, and let me show you. So if I put it into frequency measurement, so pin 5, there you go, that's 25%. That's 50%, and pin 9, 74.9, so 75%. Close enough, perfect, right? But if we go into volts AC, so we put it into volts mode, and by pressing the function we can go into True RMS or show us hertz, frequency. And when I go now and try to probe one of the signals, so let's do 6, yeah, nothing. Shows 0 hertz. But then when I go into percent, it shows me 50%, but when I start measuring, shows 0. Or anywhere else, if I try another pin, 0. Sometimes I get it to show me 100%, not sure what I did. Yeah, so the measurements, when you're in voltage mode, it allows you to go into those measurements which show frequency and, you know, the duty cycle of the wave. But yeah, it doesn't do anything. You have to have it in the frequency mode in order to measure that. But okay, it is what it is. It did cost £10. As long as you know that, it should be okay. Maybe there is something that can be modified inside to bridge those two measurements together. So let's see now which meter is closer. Let's try to work out the values. So to do my calculations, I'm going to use a cool app that I've been using for a while. I bought a full version for, I think, like £1 or £2. ElectroDroid. It's a really useful app. It's got loads of helpful calculations, just easy, you know, resistor color values through, you know, designing an inductor, how many turns, what diameter, so on, PCB trace width. It's got a lot of cool stuff, but it also has RMS converter. Let's first work out what was the peak voltage of the sine wave that we had. So when we measured the unrectified sine wave, we got about 10 volts from both multimeters, so we can agree that that was 10 volts. So I'm going to put in 10 volts over here. So the peak voltage should be about 14 volts. 14 volts peak value at 50 Hz sine wave should be about 10 volts RMS. So in both cases, both multimeters over here agreed. So now let's change the sine wave to half rectified sine wave. What we should be getting 7 volts RMS. RMS meter we measured 6.01. Now we have to subtract 0.6.7 of a volt for the diode drop, which would equal to not 7 but 6. Let's call it 6.3 with 0.7 volts drop on the diode. So a lot closer than non-true RMS. That one was measuring 9.7 volts. If we change it to full rectified, and I'm going to zoom in a little bit so you can see my post-it note a little bit better. So with a 50 Hz peak at 14 volts, RMS should be 9.899 volts. Okay, that doesn't add up. Okay, I just redid the test and remeasured, and yeah, it is showing like about 4.16 volts on the output. So yeah, not sure what's happening there. According to the app, 50 Hz sine wave full rectified at 14 volts peak should give me 9.899 volts RMS, so just under 10 volts RMS value. And let's see what's going to be in the case of the square wave. Positive square wave, so frequency 917 Hertz, I think it was. Okay, let's call it 1 kilohertz, it will be approximate, so 1000 Hertz. And the duration, we're gonna have 25, 50 and 75%. So first 250 milliseconds, microseconds rather. There you go, 250 microseconds, and peak is 5 volts because that's on Arduino. We should have RMS value of 2.5 RMS. Let's increase the duration to 500 microseconds, 3.53 volts and 750. 4.33 volts. Is it too good to be true RMS? Well, the values are nowhere near where they should be. The calculated values, actually, when I look at them, they make a lot more sense. This doesn't stack up. So, non-true RMS multimeter, the measurements are very off anywhere apart from the standard 50 Hz sine wave, where it was pretty much there or thereabouts. We did assumption actually because both meters showed about the same thing. Anywhere else this meter was off, and that's to be expected. It's not a true RMS meter. However, the RMS meter, I kinda can understand the second measurement with just a half wave rectified sine wave. 6.3 volt with versus 6.01. Okay, it could be something in my measurement, so you know, but I'm willing to accept that for the purpose of this test. But everything else is miles off. So it measured 4.16 volts at full rectified sine wave, which is less than halfway rectified. Doesn't make sense. It should be, yeah, it should be about 10 volts. 1.6, 1.95 and 1.74. Look, 50% read out more than the 75%, so it doesn't make sense. It should be 2.5, 3.5 and 4.3. You know what, those kind of ballpark figures make sense when you think about it. But yeah, the measurements on here were off by a million miles. There you go. cheap little multimeter. Actually really nice meter. Now, you know, sits nice in a hand and it feels okay, and for, you know, simple measuring stuff, the continuity meter is not too bad, reasonably quick. But yeah, the True RMS, no, unfortunately it's not so true. It's a shame. It would have been a nice meter. I mean, for £10 you can, you know, deliver it. You can't actually get a meter that does reasonable measurements, and I was hoping this would be that, but clearly it isn't. It's, yeah, it's junk. Unfortunately, £10, you can't get a value for that much money. I'm still gonna keep it, actually, you know, just for, you know, basic, you know, AC measurements and, you know, continuity, ohms, capacitance, that sort of stuff, you know. It's good for that. Even the quirk with when you go into the, I'll show you again, when you go into frequency and percentage, yeah, it's just not, why is it picking up this junk, and it's not measuring anything actually when you're doing this. It could have been such a nice meter, but they've messed it up somewhere. So if you were wondering about buying one of those, yeah, do consider the limitations. It is not a true RMS meter, even though it claims true RMS. It just shows bullshit. Thank you very much for watching. I hope you enjoyed this video and testing this meter, which sadly is not a true RMS multimeter. At least it doesn't appear so. So yeah, oops. For this video, that's it. So please do subscribe for more random electronics related stuff. For the time being, take care.